And welcome back to another video with It's Dr. Dan, and today we're going to be looking at Le Chatelier's principle. Now, what this is all about is that whenever we have a reversible reaction, meaning we have a forward and the reverse, when they are at equilibrium, it is possible to disturb that equilibrium, to apply a stress to it, meaning that the reaction can shift. It can either get pushed towards the forward or towards the reverse, and it's all based on different conditions we apply to the reaction. So the actual official definition of this is that whenever you place an external stressor on a reaction at equilibrium, it has to respond to it. So like one example to this is, if you're in your classroom and your teacher tells you, "Hey, you have a test next class," then all of a sudden your heart starts racing. That's like, "Oh no, I got to start studying. I got to prepare for this." There's all this different things that start racing through your brain. That's a stress, right? And your body's going to respond by telling you to study and prepare and respond to that. So whenever the system responds within a chemical reaction, the rate of the forward or the reverse reaction changes either to increase or decrease in order to try to relieve that stress. So we'll be talking about it shifting left, right, in terms of the reverse and the forward reaction. So now let some more examples of like exactly where do we see this? This is all over the place in everyday life. There are a lot of different systems that are in place to actually work off the ideas behind equilibrium. One of the most common ones is lines at theme parks. So if you've ever gone to Disneyland, Disney hires people to actually make different models that are pretty much based off equilibrium problems to how to try to shift the population around the park in order to give you the most fun-filled experience and the happiest experience possible. And this happens in many theme parks. So one of the things that you see the second you walk into the park is essentially an entire list of all the queue times how to get onto every ride. And usually the thing that you're looking for is you're always looking for what's the most exciting ride, and then also what is the shortest wait times. And those times are being shown to you on purpose, so that way it spreads the population around the park into different areas, right? It might say it's 5 minutes to get onto, let's say, Splash Mountain. The second you get there, you see like, oh, all of a sudden it's 15 minutes. Well, that's because people are trickling over. That reaction essentially got shifted in that direction, right? There was a stress on the park and it got shifted to a different area of the park. So that's one way to try to potentially make the reactions go faster. So that way no one's waiting in lines too much. They keep updating those times to make it faster and faster and to change the different places. Another really big example is actually with traffic too. If you ever try to plug in a destination on your GPS, sometimes it might give you your normal route, but it might say, hey, this route is going to be 5 minutes faster. GPSs are also programmed to try to relieve the stress on streets. So that way you're not waiting in 45-minute traffic if you want to go one direction versus, let's say, another direction, right? Especially if you like being there myself, I was living in LA for a really long time. This was a really common thing you would do. You'd either take the highways or the surface streets to try to avoid all the different chaotic messes that might occur. So there are different ways to try to avoid and try to shift the whole idea of equilibrium because this is a dynamic process. So it's always changing constantly whenever we're looking at equilibrium. So we're going to be looking at all the different factors in this video and trying to understand them and going through many different examples on how to break them down. All right, let's go take a look at this, and I hope that this helps you. And thank you so much for listening. Let's continue to look at the next part. So with the different factors, what we're going to be looking at is essentially, in a way, we're going to be poking the reaction with a stick and asking it, hey, can you go do something right now as a reaction? So that's what Le Chatelier's principle was all about. He essentially determined like, hey, that when he was noticing with chemical reactions that whenever we change something, the system would respond. And mainly it boiled down to about 5 different major factors that do something to the chemical reaction. It's mainly with concentration, so how many moles of your reactant or product are in the system, how hot or cold is it, the pressure and volume, so how big or small the container is. And then when you add a catalyst or an enzyme to the mixture, that's going to essentially spawn a change as well. So that's what we're going to be looking at and trying to determine how do each one of these affect these different changes and how can we exactly shift this reaction one way or another when we are looking at these. So let's take a look. The first one is all about changing the concentration in the reaction, meaning that we're going to be essentially kind of lifting the reaction one way versus another. So when we are looking at this, the way that we got to kind of think about it is similar to scales, but in terms of if we're going to be kind of like lifting one side over another. So let's say if I have the first one here and I ask you, what happens if I increase A? All right, well, A is one of our reactants. You see it's in pink on the left-hand side. So what if I increase that? Well, the whole idea is if all of a sudden I start increasing A, it's going to lead to more collisions with everything around it, meaning you have a lot of A. So essentially the probability of it finding B increases pretty dramatically. So if we increase this side, one way for you to kind of look at this reaction is almost as if you're going to be tipping it in one direction versus another. So it's getting raised by it going upwards, and it's going to be tipped. The scales tip. So when that happens, well, what direction will that reaction go? Because these increased collisions are all running into each other, the reaction is going to push forward and heavily. It's going to try to relieve that stress by making more products because the goal is for the rates to be equal. So once all of a sudden all these reactants are here, it's making it so there's going to be a lot of reaction occurring forward wise. So eventually the scales can try to tip back into place is what we're going to be seeing. So in this case, the reaction will shift right because of that stress that's placed on the system. When you have extra A particles, they will collide with B to make C and D. So over time, what you're going to see is that those scales that are like this, they'll start to slowly come back to being even after the reaction occurs. So in this case, the reaction would shift right. Let's look at another example of concentration. So what would happen if I decrease the concentration of B instead? So if I were to go through this particular reaction and I were to decrease it, well, it's going to be the same kind of concept with the reverse, right? The system's going to respond. It's going to be like, oh my God, where did all the B molecules go? It's going to freak out a little bit, and it's going to try to produce more to respond to this. So when we start to decrease that one reaction, it's going to be as if the entire system is going to try to tip itself in the direction to create more. So in this case, what are we going to see is that the reverse reaction is going to happen very heavily to try to shift it in the direction to compensate for that. When all of a sudden there's less B in the system, that means the probability for C and D to collide with each other is going to increase a lot as a result. So the reaction will shift left when that reactant is removed. The system will compensate by creating more reactants. So that means the reverse reactant will increase until equilibrium is restored. Let's go on to another. So another reaction is, well, what would happen if I remove C as soon as it forms, right? So immediately what would exactly happen? So if I keep trying to remove C from the reaction, once again, the system is going to compensate. So if I keep removing that, the reaction essentially will want to go forward as a result to make more C, right? So as we remove it, it wants to replace it. Now, the whole idea here is, well, why is that? Is because all these atoms that are in a container, in the solution or in the gas phase, they're going to be they're going to be colliding with everything around them. So if they can't find a C atom to hit, it's more likely that A and B will collide with each other. So it will shift that reaction forward to compensate. So if something is decreasing, the reaction is going to end up shifting towards it. And if something is increasing, it's going to end up shifting away from it. So that's going to be one of the ideas that we're seeing here. Let's go into another example. So let's say if I wanted to look at an actual real chemical reaction. So right here, I have iron thiocyanate, and what's happening is it's dissociating in solution. So what would happen if I add a common ion of another compound into the solution? Meaning that if you see that SCN is part of the reactants and the products, just one part of it is bound. So what would occur if let's say if I add NaSCN into the mixture here? Well, what would end up occurring as a result? Well, we got to think, well, what would happen if this molecule were to go into solution? Well, this is what has to do with your solubility rules. So if we were to add this guy, it's going to essentially dissociate into its different pieces, right? You'd have Na plus, and then you'd also have SCN minus would be the other component that would be made in solution. So you're going to have these two different pieces. So if we are creating a bunch of SCN, well, in that case, if we look at our original reaction, this side is going to be increasing by a lot, right? It's because we're making more of those ions. So how is the system going to respond? By the right hand increasing. Because of that going up, it's going to want to shift the reaction in the reverse direction or to the left in order to make more reactant, right? So if you add a common ion, it depends on like what are the different products. But being that we're going to make more SCN, it's going to increase SCN, shifting the reaction to the left. So just to kind of wrap up concentration, one way that we can really look at that, if you take a substance, the reaction shifts towards the substance, meaning if you take it away. If you add a substance, the reaction shifts away from the substance. So try to remember the T's and the A's. So if you take, it goes towards, and if you add, it goes away, is one way to look at it. So in this situation, we added SCN and it moved away from that in the original reaction, right? It moved away from it. So add, away, take, towards is one way to kind of remember it. I also like to think of it as a shifting part. So in this case, right, we added SCN. So it's like we're trying to tip the reaction in this direction. So we're going to be making a lot more FCN. It's like tipping the balances. So it's getting weighed in one direction versus another is another way to look at that too. Let's go into our next factor. So with temperature, the whole idea here is that it's going to actually be very similar to concentration. We can actually treat it in a similar respect. But before we do that, we have to remember the different labels for temperature when it came to a chemical reaction. Well, the first thing was the word endothermic and exothermic, right? Endothermic meant that heat is being absorbed and that heat is a reactant when you label it in the problem. Exothermic, heat is a product, right? And you put it as a product in that reaction too. There were different signs behind these as well. So if you remember, whenever it was endothermic, it was positive. Whenever it was exothermic, it was negative. So that's really important. And then the last thing is whenever energy, how was it measured, right? It was always in kilojoules. And then it was shown as delta H or enthalpy, which were always reflected the amount of heat that was absorbed or released in a reaction at a constant pressure. So that's one thing that we got to keep in mind too. So let's say if I were to be given a chemical reaction similar to the one before, where if A plus 2B makes C plus D, and I say delta H is equal to negative 250 kilojoules. Well, when we're writing this, you got to kind of recognize, well, is it exo or is it endo? What exactly are we doing? Because you got to write it in the reaction. And this is what I meant that you can treat it like concentration, because essentially if you're increasing or decreasing it, it's going to kind of push the reaction in a very similar manner. So let's say if I kind of rewrote this, right, it's exothermic. So that means that energy is a product. So we're going to write that on the right-hand side. So the reason I could say it's exo is because it's negative 250, right? So that tells you product. So in this case, if I increased more energy, so increasing heat, well, that means you're going to be raising this side up as a result. So it's going to get a lot hotter. So when that's getting hotter, what is it going to be essentially doing? Well, we're going to be shifting that reaction to respond to that. It's going to shift the reaction in the other direction, just like how we did earlier with concentration. We're going to raise that side up so that way it's going to shift in the essentially in the other direction, right? So when we shift that. So if that increases, we are going to shift away from it. So we will do that. So add away. So we add heat, we're going to shift away from heat. All right, so that's what will happen there. Now, what if I wanted to decrease that temperature? Well, it's going to be generally the same idea, right? If I decrease that temperature and we want the system to get a lot colder as a result, well, we can essentially say that, well, the reaction's super cold, so it's going to want to respond to that by it wanting to go in the opposite direction. So if we go really cold with our heat, it's going to respond and want to go forward to generate more heat. It's going to, once we take away a substance, it's going to want to go towards that substance, is the whole idea. So that's how we can look at temperature. Let's look at another. So sometimes when it comes to reactions, you might not be given an actual numerical value, and I'll just say, hey, there's heat involved in this problem. So with this one, it says what will happen if you increase the temperature. So we'd still treat it as exo or endothermic. So that's your responsibility to kind of remember that trend. So if it's on the left-hand side, that meant that it's absorbing heat. That's endothermic is how we can look at that. So if I want to increase that heat, well, we are going to be adding heat. So what's it going to do? It's going to shift away from it. So that means it's going to shift to the right-hand side to generate more product in this case. Now, if we had the opposite here, where let's say if I wanted to decrease that, well, how is the system going to respond by decreasing? So I'm going to make this really, really cold. Well, that means that the system's going to want to generate to try to leave that equilibrium. So it's going to shift back towards the heat direction, right? If you take it away, it's going to shift towards that substance. Let's take a look at our next factor. Pressure change. When it comes to pressure, these different changes all have to do with gases. So when we talk about pressure and volume, we're talking about different gas molecules because essentially the size of their container does affect how they react because gas particles are very, very far apart. So if a container is really small, then the likelihood of them colliding with each other increases. So it's all about how big or how small that container is, which will increase or decrease the pressure. So if I have a container with a bunch of gases in it, the reaction is going to shift to reduce pressure. Now, how can it do that? Well, it's all about the number of moles of gas. So if I'm to look at this particular reaction, you can count the coefficients. So if you see the reactants, right? So 2A plus B, I have 2A molecules and I have 1B molecule. So that means you have a total of 3 reactants on the left-hand side. And then if you look at the right-hand side, I have on my products, I have 1C and then 1D. So that means you have a total of 2 products. So that means depending on how the system responds, will essentially try to alleviate that pressure. So let's say if I increase the pressure a lot, what it's going to do, it's going to want to have less moles of gas present to make the pressure will go down. If there's a very, very low pressure, well, then it's going to try to fill that void by it going in the opposite direction. And it's also all about what are the probability of collisions occurring too. If you have, let's say, a really small container, that means a very, very high pressure, well, the likelihood of the 3 moles of reactants running into each other increases by a lot. So that's another reason why it shifts in one direction, is what's the size of the container and who you likely to run into for a reaction to happen, right? You have to, A has to run into B for that reaction to happen. C has to run into D for that reaction to happen. It's all about what is the probability of the collisions occurring. So if we were to look at this one, what would happen if the pressure were to decrease? Well, if you remember from before, where we have 3 moles of gas on the left, 2 moles on the right. So it's going to try to shift to compensate for this. So if the pressure is really, really low, it's going to want to bring it back up. So it's going to want to create more moles of gas. So when that happens, we're going to be shifting the reaction to the left in order to compensate for that, right? It's going to want to create more gas molecules in as a result of this. Another reason too is being that this container, right? It's going to be really big when it has a low pressure. The likelihood of that number of moles running into each other decreases as a result. It actually becomes harder. It's more likely that 2 products will find each other, hit each other, than it would be for 3 things to hit each other all at the same time. It's a little rarer. So it's all about trying to figure out how can you try to understand, see it. But I think the easiest way is, hey, the less moles is going to shift towards more. I think it's an easy way to look at it. All right, now what happens if the moles were equal on both sides? So I rewrote the equation, so we have a new one. So it's just A plus B is C plus D. What would happen? Well, if both are the same, and let's say increase or decrease pressure, then it's not going to favor one direction or the other. So even if you increase or decrease the pressure, there won't be any change to it. It's not going to matter. It's going to still be at equilibrium, even if you're making them really close together or really far apart, because there's no favoritism on one side or the other. There will be no change. So then that's going to be kind of one thing. Now, what if I added another gas to the mixture? Let's say it was something that's inert, like something that would increase the pressure to the mixture. Would that matter in that case? Now, well, being that it's not a part of the reaction, um, if it's actually also not going to have a change that's going to occur in the reaction because it's not a part of it. So it's essentially affecting both sides equally. So if we were to add something just as a almost like as a buffer in this case, where it's just this big gas that's all surrounding everything, once again, it's going to be no change. It has to be a common gas or a common ion to have an effect. Before we actually look at trying to understand volume, believe it or not, volume and pressure are actually very intimately related to each other. So if you remember, as pressure increases, volume decreases, and vice versa. They are an inverse relationship with one another due to Boyle's law from gas laws. So one thing about these containers that if I, let's say, have a container of gas and it's inside of a piston, right? And what this thing is describing is the reaction above where I have hydrogen combining with nitrogen to make ammonia. Now, if this container is at a full size and I want to make it smaller where I push all the molecules together, notice how close everything is together. So the likelihood of things reacting can increase immensely. So if I increase that, well, what direction would the reaction likely shift? So if we kind of look at the total number of moles here, right, I have 4 moles of gas on the left-hand side, and then I have 2 moles of gas on the right. So meaning that if our pressure goes up, it's going to want to relieve that pressure. So which direction is it going to push the reaction? Well, it's going to push it forward to make less molecules. And the way that we can see that, if we go from container B to container C, which is right here, right next to me, notice how essentially the molecules are a little bit farther apart compared to B. And that's because we have less molecules because we made more ammonia as a result. We shifted from going from just nitrogens and hydrogens like we see over here, and they're all really close together. They're going to be bouncing all over the walls. And it's going to create more reactions to help relieve that pressure to get back to equilibrium as a result. So that's one thing that we can see. The goal is to relieve stress by essentially creating less molecules in the space. So if we increase pressure, it's going to shift towards less moles. If we decrease pressure, it's going to want to go towards more moles as a result. So now let's go look at volume, which is going to be very similar to this. So the good news is that when you change volume of a gas in a system, it's actually going to have the exact same effect as pressure. But you have to try to remember that they are an inverse relationship. So you do got to keep in mind that as like pressure increases, volume's going to decrease. So you have to kind of remember those little relationships that are here, right? As one goes up, the other one's going to go down. So once again, though, the change is determined by the number of moles when we have this. And it's important to also realize that, well, what would happen if you have the same moles on each side? Well, it's going to once again be no change like before. And kind of going up to the problem we had earlier, right? That if you can see here, well, when pressure increase, volume also decrease. You can see how much smaller the space is within this piston, and it forced it forward. So it's the same relationship that's here, but you got to keep in mind that when volume decreases, it's going to shift it towards more moles. And when volume increases, it will shift it towards less moles. I think I might have said that backwards, but essentially when you have the volume decrease, it's going to shift it to less moles, and the volume increase is going to go towards more moles. So same idea as pressure. All right. So that's one way to kind of keep that in mind when you're looking at it. It's going to be the same idea as pressure. All right. So let's take a look at our last one. Catalysts and enzymes are one of the most fundamental principles around biology because it's essentially what keeps us metabolically functioning, allows us to exist. So equilibrium is a big part of how our body actually functions and works because it describes exactly how the chemical reactions within those systems work. So if I have a catalyst, what it does, it speeds up the rate of the reaction by increasing the amount of collisions. So it's going to cause things to occur faster. Now, when we have, let's say, an enzyme, the whole idea is when we have a reaction, essentially there is an activation energy barrier for the reaction to go over in order for the reaction to happen, right? On the left-hand side, we have our reactants, and on the right-hand side, we have our products. So that big hump or that big hill is your barrier. So what essentially the enzyme is trying to do is, hey, can we go around the mountain or find an alternate path in order to make that a reality? So when we add an enzyme, usually it's like going around the side of the mountain in order to make this easier to occur. It's less energy that is required. Now, the thing about this, though, is you kind of noted, you got to think that, oh, it's not only about going over the hill from one direction. There's people that want to come from the harder side too, the strenuous side. So both sides are technically easier to cross. So that means both the forward and the reverse reaction are easier. So as a result, that means that it does not have an effect on equilibrium. Overall, the whole reaction is just faster, regardless of the direction. So which is kind of nice, is that you don't have to try to predict left or right. It's not going to have an effect. Um, there are a couple important things to mention about catalysts. So the first thing is they are not reactants. They just speed up the reaction. And generally, they're not consumed or destroyed in the reaction when it occurs with the substrate they are bonding to or the reactant they're bonding to. They are just essentially assisting the reaction to happen. They're kind of being like the crane arms and the tools to help make these things actually get there a little bit faster. So the whole idea is that they provide an alternate pathway. So the way that I like to look at it is like if you kind of go, let's say, down a trail and there's a sign there that tells you all these different routes, and many of them might lead to the same exact spot, but there's different ways for you to get there, different scenic routes for you to take for you to get there. So one way that I like to always look at it is, let's say if I were to go on to different trails, well, when you are hiking, well, how could you get over the mountaintop? There are different routes. Like you could essentially go up this and maybe you could go all the way up to the very, very top of the mountain and then go over the backside to get to the other part. That's one way to do it, right? I'm sure it'd be a really beautiful hike. It's going to be really hard, but that's one way to go around it. The other way is, let's say if you're not interested in going, you don't want to go up over the mountain, you just want to get to the other side, and that's the goal. Well, maybe you could just go up the pass, which is a little bit easier. Or maybe you could even go all the way around it and go through the valley as well. There are different routes. And that's what enzymes do. They offer different possibilities to get around that peak, right? Do you want to go over the mountain, or do you just want to just enjoy a hike and go around it and have a little bit of an easier time? It's about trying to lower that activation energy barrier. Whereas this guy all the way up here, that's your activation energy barrier. That's a really huge peak to try to conquer. So it provides an alternate path so that way the system will reach equilibrium faster, is the entire idea. So that's the last part of Le Chatelier's principle. So as you could see, this was a lot of different concepts, that different factors that we could see. So let's go back to them real quick. As you can see, there was four major factors that actually had an effect on equilibrium. Catalysts and enzymes didn't. So it really comes down to knowing how these four play a role. How essentially, if I poke that reaction with a stick, what is exactly going to happen? So with concentration and temperature, they are very similar, right? If you add something to the reaction, it's going to shift away from it, and if you take it away, it's going to shift towards that substance. With pressure and volume, they have to do with the number of the coefficients, right? So the number of moles that are in a reaction. So if you want to increase pressure or decrease the volume, it's going to shift towards less moles. If you decrease the pressure increase the volume, it's going to shift towards more moles. So it's all about which relationship do you have, all right? So, and then with enzymes, it did not have an effect on equilibrium. So this has been my video on Le Chatelier's principle. So this is a broad overview of everything. I hope that this video helped a little bit understand it. And if it didn't, let me know. Let me tell me in the comments if you have questions, or message me outside of class and tell me all about it, or reach out to me via email or message me and ask for help. Okay. I hope to see you all later, and thank you so much for listening. And if this is your first time here, please hit that like and subscribe button and keep supporting the channel to help more students just like yourself. All right, this has been Dr. Dan, and thank you so much for being here. Bye now.